Let's look at linear independence now for an arbitrary vector space. Again, we had this notion for Rn when we were looking at, the subject of basically the study of vector spaces, but just for Rn when we were looking at linear transformations, et cetera, et cetera. So let's start with now, again, V just being an arbitrary vector space. We'll recall the definition, but tweak it a little bit for to be more general here. The collection of elements V1 through Vn, right? This is a subset of V, is linearly independent if we have the linear combination C1V1 plus C2V2 plus blah, 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 plus CnVn is equal to 0 implies that all of the coefficients are 0. So C1 equals C2 equals et cetera, equals Cn equals 0, right? So meaning there is no way to write C1, or excuse me, there's no way to write any of the vectors Vi in terms of, or as a linear combination of the other vectors. So the only way this is equal to 0 is if every constant is equal to 0, right? Because if there's some non-zero constant, then you could write one of these vectors in terms of, or as a linear combination of the others, that would be linearly dependent, right? And so we do not have that for linear independent sets. And again, so otherwise, here, maybe I'll write it just at the very bottom. Otherwise, the collection V1 through Vn is linearly dependent, right? And that just means at least one of the vectors in the collection V1 through Vn can be written as a linear combination of the others. Let's look at an example in a vector space that's not just Rn, right? Let's look at the set. Let's ask, is the set S given by x squared plus 2x minus 1 comma 2x squared minus x plus 3, is this set contained in P2 linearly independent? Right? Well, what do we need to do? We need to show that for any linear combination, so kx squared plus 2x minus 1 plus L 2x squared minus x plus 3 equal to 0. This is only true if k and L equal to 0. So we have to go through some process here and show that this is only true if k and L are 0, right? That's sufficient to show that this set is linearly independent. If we can find a solution to this where either k or L are non-zero, then we'll know that it's not linearly independent, okay? So let's just go ahead and start here. We can distribute twice on the left, so we're going to get kx squared plus 2kx minus k, and then plus 2lx squared minus lx plus 3l is equal to 0. Again, we group like terms, and we're going to get k plus 2l x squared plus 2k minus l x, and then it looks like plus 3l minus k equal to 0. But what is 0, right? As a polynomial, if you would like, 0 is equal to 0x squared plus 0x plus 0. Now, we can get a system of equations by setting up that the coefficient of x squared on the left must be the same as the coefficient of the x squared term on the right. And so we get k plus 2l is equal to 0. And we do the same thing for the linear term, which means 2k minus l must be 0. And we do the same thing for the constant term, and we get that 3L minus K must be 0. Now, what we have to do, or what we're tasked with doing, is solving this system of equations and showing that the only possible solution is 0, 0, right? So we have, looks like we're gonna have 1, 2, 0 for the first row, and then 2, -1, 0, and then -1, 3, 0. Right? Because the third row there, I swapped K and L. Maybe it was more convenient to write it the other way. But we put this in reduced row echelon form, right? And exercise for you, we get, let's see, what did I get? I get 1, 0, 0, 1, 0, 0, 0, 0, 0, which implies K equals L equals 0, which implies that the given set here, let me call it S so I don't have to rewrite it. This is a set S. S is linearly independent. Cool. Now, we've seen an example here, and if you'll remember, whoops, we had a uniqueness statement about, in linearly independent sets, how you can express other vectors as linear combinations of those linearly independent elements. So here's a theorem on the uniqueness. We have, let's let U, well, let's say U, which is given by U1 through UK. Let's let this be a subset of the vector space B, and let's let this be a linearly independent set. So be a linearly independent set. For every V in the vector space, well, rather in the span of U, right? So for every vector V in the span of U, there exists uniquely constants C1 through CK in R such that V is equal to C1 U1 plus C2 U2 plus blah, 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 plus CK VK, right? So this is saying if you have any element in the span of a linearly independent set, the representation of that element is unique, right? So what can we do with this? Well, we can prove the following lemma. We have that if for some vector v not in the span of, say, u1 through uk, and u1 through uk is linearly independent, then u1 through uk, and if you add v to the collection, then this is also linearly independent. So this is a good way of extending linear independence, right? Or, you could really, what this would be doing would also be extending the span of a linearly independent set, which would also be extending a basis, right? If you remember that if you have a linearly independent spanning set, that is the basis for the subspace generated by the span of those vectors, right? Well, that means if you're adding a vector that's also linearly independent, that's not in the span of those, well, then you're extending that basis to some new span, right? Which is a very important concept. So let's prove that we can do this. Proof. Let's suppose that we have C1 V1 plus C2 V2 plus et cetera, plus CK U, well, rather U, sorry, I've been using U for the set U, so I better stay consistent. C1, U1, C2, U2, CK, UK. And then we're trying to show that this set is also linearly independent. So let's also throw in like this plus dv equals 0. And again, this is for the set U1 through UK, and we're assuming, so let's suppose that V is not in the span of U1 through UK, right? We're assuming that. And we're considering, so like suppose V is not in the span, and then consider the following equality here. And what we're going to do is we're going to approach via contradiction, right? We're trying to show that the set U1 through UK V is linearly independent. So by way of contradiction, let's assume that it's not, right? Let's assume that D is not 0 for the sake of contradiction. Right? Because if we assume D equals 0, well, then that would be assuming what we're trying to prove, which we can't do. We know C1 through CK is linearly independent. So if you were to kind of get rid of this term, we know C1 through CK would have to be 0. So our contradiction, we're going to unearth a contradiction from assuming that D is non-zero, right? Which would mean that this is not a linearly independent set. Well, if we assume that, then we can write C1U1 plus C2U2 plus blah, 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 plus CK UK is equal to negative dV. Well, this step we could do even if D was 0, but the next step we have to rely on the assumption that D is non-zero, and we can write V as negative C1 over D U1 plus negative C2 over D U2 plus et cetera, plus negative UK over D UK, right? But what does this expression mean, right? If we can write this for some non-zero D, well, we've just found constants such that V is a linear combination of elements in the set U1 through UK. So this equality implies that V is in the span of U1 through UK, which is a contradiction. And since we have a contradiction, that means we do not have that the set U1 through UK V is linearly dependent, therefore it must be linearly independent. So end of proof, right? Great. Let's wrap up this with an example here. So let's let S be the following set of vectors, vectors because it's in a vector space, but in particular the elements are matrices, right? So 1, 0, 0, 0, and then 0, 1, 0, 0. Let's let this set be a subset of the collection of all 2x2 matrices. First, I have a challenge for you, or an exercise, is to show that this set is linearly independent. And what we're going to do together is, once you've shown that, then let's show R, which is the following set: 1, 0, 0, 0, 0, 1, 0, 0, and also 0, 0, 0. Whoops. 1, 0 is also linearly independent. Right? Okay. So, and basically, what is this doing, right? We haven't got to the discussion of a basis yet in a general vector space, but this is extending a basis, is really what this is doing here. Okay, so by the last lemma here, what we have to do is we just have to show, right? Because by now we are able to use the assumption that this set is linearly independent, which is the same as the first two vectors in the set R. So by the previous lemma, it suffices to show, or it suffices to prove that 0, 0, 1, 0 is not in the span of S, right? And then we can apply this lemma that we've just proven to show that R is also linearly independent. Great. So what do we need to do then? That means we need to show that for every constant K and L, the following equality cannot hold. So I don't know why I wrote S. So K times the first element of S, that's why I wrote S, plus L times the second element of S, which is 0, 1, 0, 0, right? We need to show that this does not hold for all K and L, and that would show that the element 0, 0, 1, 0 is not in the span of S, which is the collection of these two, right? Well, then this is K 0, 0, 0 plus 0, L 0, 0, which is KL 0, 0. But you can see again, for two matrices to be equal, every entry has to be equal. This implies that 0 equals 1, which implies that this is an inequality for all K and L and for reals, which implies by our lemma that R is linearly independent, right? Because we've shown that this element is not in the span of S, right? And so since it's not in the span of S, we can conclude by this previous lemma that that collection R is linearly independent. Okay, so this will wrap up our discussion and examples for looking at linear independence and understanding linear independence in a more generalized setting.